Maganahalli, and so over the past 6 weeks, underneath the direct supervision of Dr. Kenneth Shackle and my graduate mentor Brian Chen, I've been doing research upon the material failure that occurs during the process of fruit cracking. Simply put, fruit cracking is a process that exposes the flesh of the fruit to the external environment, and because of this, allows for infections and other things to happen, ruining the fruit and stopping it from being consumed. And so, in commercial fruit production, this is a huge problem. As you can see in the graph above, 50 to 60% might be consumed in the end, produced from the harvest that you eventually get. However, 10 to 15% of the fruits here aren't actually even produced because of the fact that they're ruined solely from the process of fruit cracking. And fruit cracking is a major problem because of these problems listed. For example, it could be a breeding ground for fungi and pests. It could be a breeding ground for viral infections. It can also cause losses in future generations and a loss of resources put into it. This is exacerbated by the fact in areas like California, for example, where there's a drought. With the amount of water put into it and eventually lost because of the problem of fruit cracking, this exacerbates the problem that already exists. Additionally, in areas that don't necessarily have that many resources to begin with, this causes problems with things like fertilizer and mulch. And so, it's not that people haven't done research on why fruit cracking could occur. I mean, they've come up with all these reasons for why it could occur. Yet, there's no single fundamental reason for why it could cause it. And so that's why there's no real treatment for it. And so what we've been trying to do in our lab is to say what happens during fruit cracking so that we can trace back to why. And since nobody has actually found the why, this is the best process forward so far. So, why we're doing the what? What should happen during the expansion of the fruit is that it should open up like a balloon. If we put water in the berry, it's like putting air into a balloon. It should expand, and the ratio of the distances between different points upon the berry's surface should expand linearly. But that's not what happens. The blue dots that are now overlaid are what happened during the berry's expansion. Once the crack appears, this material failure that occurs, the areas close to it will actually contract, rather than expanding linearly across the surface. Whereas areas further away from it will stay relatively similar to where they were before. So why is the area closer to the crack actually contracting? That's the real question that we're asking. And so what we do to simulate this, first we begin by choosing berries of different stages, pre, post, and during veraison. And I'll go into what veraison is after this. Next, we freeze it for future use, and so that we can do it on different days, since it takes nearly 16 hours to induce cracking. We spray paint dots onto it so that we can track the surface and see how exactly it's moving along the way. We submerge the berry and then induce the cracking by putting water into it and submerging it completely in water so that it continues to absorb it until it cracks, since water stress is a major source of cracking. And then we do time-lapse microscopy, which tracks the berry and the dots upon it so that we can see what exactly is happening during the process. Next, we enter the dry lab phase, which is mostly where I do most of my work. So, time-lapse imaging, as I've already stated, is just run through a process called ImageJ. It's a program produced by NIH that allows us to track circular dots on the berry surface, and so we can see the relationship between them as they move across the images. This is extremely rough software, and it's not necessarily the best. You need to pick very similar dots, which is why it's so restricted in the relationships that we can choose, but it fits its job just fine. The text file that is eventually produced is then put into the UC Davis S drive. What this does is it allows for all the faculty data and every data that I produce to be put onto a local area for other people to examine and then later analyze. Next, we put the pairings listed on Excel. Then we use the Excel and text file put through SAS, which is a software program that, much like the Unix and Pro that Eric and Jack had to learn, I had to learn how to use it, just not to the depth as much as them. And next, we use the graphs that are produced from SAS to detail the movements produced. So, coming back to veraison. Why is veraison so important? Well, veraison is how much sugar content there is within the berry. I'd like to draw your attention to the center here, which is where the veraison actually occurs. As you can notice, after veraison, there are large purple berries, rather than the small green berries that existed before. And so what this actually signifies is that there's a rise in sugar content within that, which is what produces the firm purple berries that you're so used to eating. Next, you can see here that this is the kind of stuff I work with. The text file is a bit unformatted since I work on a Mac, and this is a PC desktop, and then this is the Excel file that we use. This is just quick relationships. And then this is the kind of programming that I do. We just plug in the files that we have, and it runs it for it. So, what exactly are the graphs that we use? Well, to begin with, they're all very similar graphs, so I'm just going to go over them in a rough template. So we'll begin here at the time on the x-axis. So we begin at 0 hours, and we use 16 hours and 40 minutes as the end of the x-axis. The reason it's such an abnormal time is because this is actually 200 images in 5-minute intervals, which is why it accumulates to 1640 or 1,000 minutes. And so the strain is the y-axis. Notice how the 0 if it's a positive strain, that means that there's stretching between the points. And that indicates that there's actually a strain or pulling apart right there, and that's causing it to become closer and closer to cracking. And a negative strain would mean that it's actually contracting. The points are getting closer and closer together. And the zero means that there's no strain, or that it's perfectly balanced and nothing's actually occurring between those 2 points, which is very, very, very rare. And so at this point, this is the time of the crack, and this is where you'll see most of the graphs changing values if they change at all. Additionally, the strain before the crack and the strain after the crack also matter a lot. The strain before the crack will signify how much strain there is before the crack actually appears, and why it may be causing that because of how much strain there is before that. Additionally, the strain after the crack also shows in things like perpendicular relationships, as I'll go into later, that these kind of areas that go negative or positive, that there's still strain being imposed on it, or there's actually strain being lost from it. So the graphs you'll see now are the kind of relationships I work with. Here are the first 2 of the 4. This is an across the crack graph. As you can see, it's very typical. It goes straight up almost most of the time. It could be like as much as 60 up to 160, and these are very, very large graphs. Whereas in comparison, there's 3 to 4, and then from here there's 0.33, and then 4, 6, 7. So clearly there's a large gap between this kind of strain and this kind of strain. Additionally, in a perpendicular crack area, what this means is that perpendicular relationships are brought at a 90-degree angle to the actual crack. And so what this means is that these kind of areas show that there's a strain next to the crack area, or an area that is located near the crack. Parallel non-crack barriers are, on a non-crack barrier, since there's no crack, you can only take parallel strains. There's no such thing as a perpendicular strain, since there's no actual crack to be compared to. And lastly, on a parallel crack area, what this means is that on a cracked barrier, where there is a crack, in the area close to it, there are still parallel strains being taken, and these are the kind of graphs that we produce. So let's begin with perpendicular strains that cross the crack. So over here, you can see that across the crack, there's clearly this skyrocketing graph. It goes up to 160 in a value of the strain. So what this means is that there's an explosive strain growth, and that's because the crack is growing. So that means that the crack, if the crack is clearly growing, that this area should be growing too. But that's not what happens, and this is why it's such an interesting topic. It's because these areas are actually showing negative strain after the crack occurs, but show positive strain before it occurs. So what this means is that there's strain occurring before the fruit cracks, but there's negative strain and contracts afterwards. And so the leading hypothesis on why this occurs, rather than staying a positive strain, is that they're actually dead cells, and so the turgid cells that grow from the crack actually expand and close off the dead cells, and so these dead cells end up contracting and closing the distance between those 2 points, producing the negative strain that you can now see on this graph. But now, after doing parallel relationships, which we have not done before, this is the first set of data on these. We've taken 3 varies for these kind of cracks, and then for parallel or perpendicular, we've taken 7 sets. But in these 3 sets, notice how there's never really a negative strain on these. It starts off positive and continues to stay positive. At some points, it peaks to a negative area, but eventually comes back to a positive strain. What this means is that it's continuing to grow and grow and grow, and there's no actual contraction, which is very interesting when you notice how close it is to the crack. There's no contraction in the area that close to the crack, despite the perpendicular relationship showing such contraction. So if this is true, then why exactly is that occurring becomes the next question. And so we analyze this on a non-crack barrier, which is the other kind of barrier that we really evaluate. Because if we only test the crack barrier, this would show this, but if on a non-crack barrier, it would show the same results. I mean, clearly it's constantly true for all of them. But as you can see from this, it starts off positive and then drops negative. It can go positive, and it shows all sorts of things. Noticeably, these kind of up and down lines are usually due to the technology not being able to recognize the dots at some points and produce these kind of shaky lines, but eventually follow like a relatively similar pattern. But what I'd also like to draw your attention to is how big the strains are. The biggest strain you can see here is a 4. Everything else is on a very, very small scale, less than 0.5. And so if that's true, that means that on the only large scale that there's a positive, and everything else is barely moving. So that means that there's very little strain actually occurring upon a non-crack barrier, which means that there's nothing actually really holding or pulling it apart. So what does this mean? Let's begin with the perpendicular contractions. If there's only contracting on a perpendicular strain, that only means that the area close around it would actually be contracting. There's nothing actually happening on a parallel strain. So the barrier would be extending like this rather than actually contracting on all areas as it should be. So this produces the anisotropic behavior. What this means is that there's different properties on the barrier surface. If there's different physical properties, that would explain why exactly in some areas it might be contracting, and why in some other areas it might be cracking, and why in some other areas it just doesn't happen at all. This also incorporates for the stretching that occurs as well. If there's different properties across different fruits, and there's different properties in different areas of the fruit, that could be why these kinds of things are occurring in different areas, rather than actually occurring in all the similar areas and happening across different areas. so where do we go from here? So currently we're working on a full skin scan at the same time. Rather than taking these small little strips at once, we're working on a full area using triangles and area plots. Rather than taking these small lines and saying, okay, the relationship between these two dots are moving currently, we can take the full area of the entire berry, which we currently can't do due to the inability of image J. But with this, we can run this entire area and see how the entire berry surface is responding to this cracking, rather than seeing how small areas are. And again, we trace the what back to the y, and this is big because it's not a y to the what. We're finding what occurs during this berry's process so that we can trace it back to the y and eventually provide treatment for it that is currently unavailable in the markets. And so for acknowledgements, I'd like to thank Dr. Ken Shackle and Brian Chen, my mentors for this lab, and who really led me across this project. I'd also like to thank Dr. Mark Matthews in the Department of Viticulture, because he also helped as well, especially with department meetings. And from my state, I'd like to thank Dr. Ray Pomeroy and my counselor here. So how and what units of strain measure? So units of strain measure are just like distance, basically. It's just like how far apart. Yeah.
Would you say there's any benefits and advantages to fruit cracking or detrimental?
Sorry.
Would you say that there are any benefits to fruit cracking, or is it just detrimental to the fruit?
No. From what I read, it's only detrimental because of the reason that it provides so many things like training grounds for pests, and it also includes viral infections, and it just basically harms the crops in general.
Are there certain fruits that are more susceptible to fruit cracking than others?
So she has said certain fruits are more susceptible, and so it just depends on the fruit in general. As I say, there's so many reasons that it could occur that, like, they've said that our fruits can crack more readily, like cherries or things like that, but it's not necessarily true. All fruits can be susceptible in different environments, and so that eventually causes viral infections.
When you say that cracking causes the fruit to be more prone to carrying infectious diseases, is that for the fruit, or if humans were to eat that cracked fruit, that would possibly trigger?
It's usually for the fruit itself. I mean, they would restrict you from eating it, which is why they don't want you to eat it because it would be a fruit, and like again, fungi and other things could also be in it, as well as the infections. So they just prevent you from eating harmful things.
The cracking usually occur while the fruit is still on the tree, or when the fruit is hard?
So she asked whether cracking usually occurs on the tree or afterwards. So again, it really links back to aeration. And so as I say, the aeration is when the sugar content rises and like really becomes ripe. And so it usually happens after that because the fruit becomes much firmer, and it's just like a lot more like the skin becomes a lot more susceptible to actually cracking since it's being stretched even further. So because of that,